Okay, so here is lesson number 4 in the whole electrical saga. There are some other equations that you need to know here. There's more than the ones I'm going to do today, but there are 2 more equations really that you need to know around the material we've been doing. And I want to extend the work that we did on Ohm's law to look at potential dividers. So the relationship between current and charge, you'll remember we said that current is the rate of flow of charge. Now, if we say that charge has a symbol Q, and that's measured in coulombs, which has a symbol capital C, then current, as we know, symbol I, and measured in amps, symbol capital A, then the equation Q is I times T. Now this comes from what we have up here. Current is the rate of flow of charge, so current would be the charge divided by the time. What I mean is, if you had 5 coulombs which flowed along a conductor over a period of 5 seconds, then the current, which is the rate of flow of charge, the charge per second, is the number of coulombs divided by the seconds it took for those coulombs to flow, 1 amp. Okay? So there's an equation you need to know, be able to use, and be able to rearrange. Over here then, energy and potential difference. We said that potential difference is the work done per unit charge between 2 points in a circuit. And you'll remember that work and energy are the same thing, and they're measured in joules. So PD is the work per unit charge, so V, the PD, is the work per unit charge. We could say that work is given the symbol W, or equally we could say energy, because work and energy are the same thing, capital E. So V then is the work done per unit charge. You might also see that as E divided by Q, because E and W, energy and work, are the same thing. So if, for example, you had a PD of, let's say, 12 volts, and you had 6 coulombs that were moved through that 12 volts, then the work done, which is from this equation V times Q, 12 joules per coulomb times 6 coulombs, 72 joules. Okay, so you have really 2 equations, Q equals IT and V is W over Q. You can have these in words, of course. Charge is current times time, potential difference is work done divided by charge. But those are 2 equations that you need to know and be able to use. And as I said, this equation and this equation are exactly the same because work and energy are exactly the same. So moving on then to the sort of third element of what I wanted to say, potential dividers. You come across these perhaps in the more difficult questions that you come across. Not that they're difficult particularly if you understand what's going on, but they look more difficult. So there I have a battery made up of cells. Let's say that's 12 volts. You'll notice I like 12 volts because it's easily divisible by several different numbers. So let's say we've got two resistors. And I'm going to save me drawing this too often. I'm going to label these R1 and R2. Now, what we said about potential difference before was that the total rise from positive to negative is 12 volts. So just go that way. And the total drop this way is 12 volts, right? So there's a gain of 12 joules per coulomb, and then there's a loss of 12 joules per coulomb going around the circuit. Now, however you get from here back to here, going around the circuit, you're going to drop 12 volts. So if we had scenario 1, R1 and R2 are the same, well then half of the potential difference will be dropped across R1 and half of it across R2 because they're equally difficult to get through. So the PD across R1 will be 6 volts and the PD across R2 will be 6 volts. Now, if, let's say, R1 was twice as difficult to get through as R2, then twice as much energy per coulomb will be lost going through R1. So 2/3 of it will be here and 1/3 will be here because twice as much is here as here. So the PD across R1 would be 8 volts and the PD across R2 would be 4 volts. So with these nice easy ratios, it's easy to work out. But what you might say, or what you might end up with, are two numbers that are not multiples of each other. So if you said, for example, R1 was 10 ohms and R2 was, let's say, I don't know, 15 ohms. Now, whilst you could do this ratio business, it's not as easy. So let's say I will make it 14 ohms because that is going to be easier to calculate. So the ratio was not so easy to do here at all. However, we could say from Ohm's law, V equals IR in order to work out the current. So we say, well, we've got 12 volts. We have the current flowing in that circuit, I'll just label that up there, times the total resistance, R1 plus R2, 24. You can see now maybe why I picked 14 rather than 15. So the current would be 12 divided by 24, which is 0.5 amps. So now we know the current which flows through these, and because they're in series, it's the same current through both. We can then say that the PD across R1 is the current through R1, 0.5, times the resistance of R1, which is 10, which is 5 volts. And the PD across R2, well, that has to be 7 volts, but we're going to see that. 0.5 times 14, that's the current, times the resistance, V equals IR, gives us 7 volts. Now that had to be 7 volts, because that had to be 12 minus 5, because this plus this would always give us 12. So there's your potential divider. Basically what you've got here is a way of stepping off, if you like, some portion of the supply PD. This being my supply PD, some of it is dropped across here, some of it is dropped across here. This plus this equals 12. So if we were to make this a more practical, more versatile arrangement, rather than having two fixed resistors, we could have a variable resistor and our 12 volt supply. I'm not going to do any calculations on this because the calculations are the same. But now you see the PD across here depends on what I do here. So I could connect a light bulb out here maybe, and as I turn this, I change the PD dropped across here, and so my light bulb comes on. It's bright, it's dim, depending on what I do with this. So that light bulb could be, or I don't have to have the light bulb out here, I could just make that my light bulb. Or I could have my variable resistor, or my resistor, sorry, and I could have my LDR. I'll make it variable. Got my 12 volts, eh? As I said, I like 12 volts. So my LDR could have a lamp out here, and when it's light, the resistance of this is very small, so the PD across here is small, and so the lamp doesn't light. But when the light falls, less light hits this, the resistance rises, the lamp comes on. Now I can use my variable resistor to change the light level at which the lamp comes on. If I make this resistance bigger, then less of the PD is dropped across here, and so it needs to get darker before the lamp comes on. Conversely, if I make this resistance smaller, the light will come on earlier. And you can do the same sort of thing with a thermistor. Same idea, where you have the heater or whatever, the fire alarm coming on when the temperature rises, the resistance of this falls, and so the fire alarm goes off when, as the resistance of this falls, more and more of the PD is dropped across here until your alarm goes off, which would be a buzzer or something. So you could use it equally as the temperature changes to turn on your central heating. So this could be your thermostat. So as the if you take your thermostat out here to your central heating, to your motor maybe, then as the temperature falls, the resistance of this gets larger, turns on your motor to pump the water around your central heating, turns on your burner. So these are all potential dividers in that they're all dividing the supply potential into two. Not two equal parts, but into two. So there it is. And there's two approaches to the potential divider. There's a nice simple ratio approach, which you can do if that's available to you, if the numbers allow you to do that, or you can work out the current, then you can work out the PD. And this is what you're most likely to be expected to do in the exam. Okay.